Okay, now one of the things in equilibrium is called the common ion effect, and this is to do with the fact that up to now, when you've put something like silver chloride into a solution of water, it's been pure water, there's been nothing but water, so when the ions dissolve, there are no silver ions in there are no chloride ions to start with, and so we get this equilibrium between the solid eventually when it forms a precipitate and we get a saturated solution, and the chloride ions. Now, that's not always the case. What if there's a solution of hydrochloric acid? That means there's already going to be some chloride ions, as well as some hydronium ions, but they're really a little bit irrelevant because they're not going to do anything to the silver chloride, they're just going to be there. But because you've already got chloride ions there, that means there's an increase in concentration of chloride ions, so the equilibrium will shift to the left, and the solubility will decrease. So in common ion, quite often in NCA, the question's about to do with how the equilibrium is affected, or how it's affected by having something there. Now, just as easily we could change that and have something else there. So these questions are usually easy to recognise that they're talking about a solution which already has something in it. So if it was silver nitrate, there'd be silver ions floating around and there'd be nitrate ions floating around. So when you place that in there, there would already be now, because there's already silver ions present in this case, it means there are a higher concentration of these, which means the equilibrium would shift to this side. Now, and that would decrease the solubility. Okay, so the Ks value would always be the same, it's just the solubility that changes. So we would say that there would be a decrease in solubility. Okay, now, there are sometimes calculations you can do on common ion effect. Now if we look at the normal situation of silver chloride and it dissolving into the silver ions and the chloride ions, in pure water, if we just took the square root of the Ks, we'd get this as being the solubility in moles per litre. Now, if we now try and put it into silver chloride, we're trying to put silver ions and chloride ions into a solution which already has chloride ions floating around. There are sodium ions obviously already there as well, but they have no effect on how much silver chloride dissolves. So if there's already chloride ions in there, how is that affected? Well, we can do a calculation if we know the concentration there, which we do. So the Ks value does not change. So we put that in as the Ks, and that's going to equal the concentration of the silver against the concentration of the chloride, which we're going to put as equal to 0.025. Now, if you're thinking about this, you'll be aware that if this concentration in here is equal to 0.025, and we're adding chloride ions to it, surely that means that the actual concentration of here, the chloride ions, is going to be more. It is going to be more. But we can ignore that a little bit more that we're adding here because it's such a very, very small number. Okay? So it's one of those things that doesn't really affect it. So what we're really trying to work out is how much of this will dissolve, and we end up working out the concentration of the silver ions that go in, and we say that's going to be the new solubility. Okay? So now if this had been a squared, obviously we'd square this number, and if this was squared we'd have to take the square root of it, okay, once we'd finished the calculation. So, but at this stage, if we just divide that through, we go 1.6 times 10 to the negative 10, that's the constant, and we divide by 0.025, that will give us the new S. Okay, so 1.6 exponent, negative 10, divided by 0.025, and that equals 6.4 times 10 to the negative 9. Now, we can make a comparison between these values. This was the solubility in water, and this is the new solubility in a solution that already has a concentration of sodium chloride, and we can see that solubility has decreased significantly, which is what we would expect. Okay, so that's how you do some of the common ion calculations. Alright. just one thing to take care of. In this case, we've got calcium hydroxide dissolving. If they told you what would happen in a solution at a pH 9.9, they're actually telling you in a roundabout way that there's already hydroxide ions present. You just have to calculate the hydroxide ion given the pH. So you've got to be used to doing those pH calculations. That's one additional thing to watch out for with common ion. Okay, now I just thought I'd throw in here a case of a question which is one that isn't immediately obvious. It's asking, what is the minimum concentration of I- ions to precipitate PbI2 from a 0.02 mole per litre solution of lead nitrate? And it's given you a Ks value for that precipitate. Now, as soon as you see the word precipitate, most students start thinking in terms of this is one of those precipitate questions, which is the IP going to be greater than the Ks? Well, the first thing in all these questions, including the normal precipitate questions, is to write out the expression for what you're interested in. By expression, I mean, for instance, the one for the precipitate. So that would be Ks equals Pb2 plus I minus, okay, and that's squared. Now they're saying this is a solution of PbNO3 so that means there's Pb2 plus ions and nitrate ions. Now that should start you thinking that there's already a concentration of lead 2 plus ions, okay, so that concentration there is going to go in there, and the constant here is going to be used there. And what we're working out here is the concentration of the I minus, which is what it's talking about. So if we go through and do that calculation, it's going to be 7.47 times 10 to the negative 9 equals 0.002 times I minus squared. And if you go through and do that working and check it on your calculator that you can do it, you should get 1.93 times 10 to the negative 3 moles per litre. Okay, so when that goes, okay, so this is going to go over to that side and get divided into here, and that's going to equal I minus here squared. You have to take the square root to find this answer here, and that's your final answer. Okay, so I just thought I'd throw in a question which isn't immediately obvious as being a common ion one, but it is. Okay.